Good afternoon, ladies and gentlemen. We're going to start the webinar of today. Today's webinar will be about the economics of energy flexibility. Today's agenda is as follows. I'll give a short introduction about the webinar, about the Energy Flexibility Forum, on which the webinar is a prelude. And then Cara Goldenberg of the Rocky Mountain Institute will give a presentation on demand flexibility and how it's key to enable a low cost and a low carbon grid. After that, Héloïse Hoyos from Ensight will give a presentation on how you can reduce your energy bill with flexible production planning. And after that, we're going to have a shared Q&A, and then the webinar is going to end. As I said, the webinar is a prelude to the Energy Flexibility Forum we will host in June in Copenhagen. In this forum, we will bring together all different stakeholders in the energy chain, and we're going to discuss flexibility. I think the good thing about this forum is that we won't just talk about the need for flexibility and showcase the different solutions, but we're really going to bring together all different stakeholders in networking activities such as roundtables and networking lunches to really further this agenda. Good to know is that the early bird is expiring this coming Friday. For you as a webinar participant, you can save an additional 10% by using the promotion code webinar-10 for the registration. Some practical notes for today's webinar. If you have technical issues, please use the chat box, not the question box. For questions, you can use the question box. As I said, the Q&A will be a shared Q&A. You can address your questions either in general or to a specific presenter of today. And the presentation slides will be available afterwards. So it's a pleasure to introduce you to our first speaker of today, Cara Goldenberg. She's an associate for the Rocky Mountain Institute and will give a presentation on the economics of demand flexibility. Her focus is on regulatory policy reforms and changing utility business models in the energy transition. So Cara, I'm going to hand you over the controls of the screen, and then we're going to start your presentation.
Great, thank you, Thomas. Hi, everybody. Thanks for joining the webinar. As Thomas said, my name is Cara Goldenberg, and I work with the Rocky Mountain Institute. And today I'm going to discuss a report I wrote with my colleague that was published back in February, and it is called The Demand Flexibility, the Key to Enabling a Low-Cost, Low-Carbon Grid. And so for the next 15 to 20 minutes or so, I'm going to first say a little bit about the context on why we decided to undertake this study, describe what we mean when we say demand flexibility and what we see as the opportunity, walk through a little bit of the framework and the modeling approach we used in the report, and then end with the key results and the implications we see from those results. So, sorry, I'm having some difficulties. Changing slides, there we go. So why is demand flexibility important to consider in both resource planning and when determining the investments you want to put in on the grid? So right now, the US and many other countries in the world are relying on an aging fleet of generators. If you see on the left, this is the stack of operating generators that we have in the US right now. And if you start looking at when these units are going to retire based on their age, you're going to see that more than half of the nuclear fleet will be retiring by 2030. More than half of the coal fleet will be coming offline, and about half of the gas fleet will be offline by 2030. So that's a lot. That's a huge gap in our energy system that we need to start planning for. And to my understanding, the similar trends are happening in Europe with a lot of countries retiring coal. So how are we going to fill this gap? Here we go. And a great opportunity is looking like renewable energy. And so we see here the dramatic price decline of wind and solar over the last 10 years and the forecasted decline for the next 20 years. These resources are becoming a new default choice for new energy investments. However, we have already begun to see some issues with the rapid penetration of renewable energy. So this chart is from Bloomberg New Energy Finance, and it shows the realized revenues of solar PV projects in California since 2011. So this x-axis over here shows how much energy was provided from solar in California over the years. The dots show the various years. And the y-axis shows how much the revenue solar projects earned in California relative to the average wholesale prices realized that year. So as you can see in 2011, 2012, when solar was only providing about less than probably 1% of generation, it was earning about 25% above that average wholesale market price. And this is largely because it was mostly generating in those times of the day with peak prices. But as you can see, by the year 2017, solar is now providing about 9% of annual energy in California, but is making 50% below that average revenue. And so this has stirred a bit of a craze, and a lot of folks have been quick to say that this means that there is an economic limit to variable renewable energy penetration. And I'll discuss a little bit of why we see this. So this graph shows a marginal supply curve of energy. It is supposed to be representative of the ERCOT market, which is the grid system in Texas. The x-axis here shows how many gigawatts of generating capacity are available to produce energy. The y-axis shows how much it costs to produce each unit of energy. That's the marginal cost. If we draw a line to show demand, here we go. Where they intersect, that is the price at that hour of the day for every generating unit. So what if you have high renewable penetration on the system? This pushes the net demand to the left. And this is because the variable renewable energy reduces load that must be met by thermal generators. So that marginal cost to meet load declines accordingly, and pushing the clearing price down and causing generator revenue to fall. However, this is where demand flexibility can come into play. And so, first off, I want to explain what we mean by demand flexibility. Demand flexibility demand flexibility, in short, leverages the opportunity to shift load to better match the supply of renewable energy. So by using new communication and control technologies, demand flexibility allows loads to continuously respond to changing renewable supply levels and other market signals. So here we see a load of a simulated residential customer in Hawaii with PV. And we can see how this load corresponds with the supply of solar throughout the day. This top profile shows the business as usual changes in household energy use throughout the day, while this low profile here, this bottom profile, shows what can happen with demand flexibility using smart EV charging, smart water heaters, etc., you're able to shift that consumption into the middle of the day when the PV generation peaks. And so beyond the household, though, demand flexibility has significant benefits at the grid scale. So as I described earlier, high penetration levels of variable renewables lowers that price on the wholesale market. However, demand flexibility can mitigate this impact on price. By increasing demand at times of high renewable availability, demand flexibility increases that clearing price of renewable energy and thus the resulting revenues of renewable projects. And so what's out there today? So traditional demand response programs have been around for years, and these programs usually send customers consumer signals to reduce energy consumption during times of high stress on the grid. And so these new demand flexibility programs, in contrast, they take a different approach. Instead of focusing on curtailing that energy use, demand flexibility actually shifts energy use while still maintaining that same level of daily electricity consumption. And so here we have two different programs. One is using ice bear storage, and one is using grid interactive water heaters. Grid interactive water heaters are a great source. We have a lot of them here in the US. About 50% of the water heaters are electric, and so basically there is a potential for those electric water heaters to interact with the grid directly, basically idle batteries waiting to be utilized. And so these programs were designed to address peak load, also benefit distribution operations. In both of these programs, the utilities control the technologies in the aggregate, so and under certain parameters that customers agree to. And so this brings us to our study, which is what role can demand flexibility play in a future with high renewables on the system. And so our paper wanted to look at the potential demand flexibility can have in a high renewable ERCOT system. We used ERCOT because, and once again, that's the wholesale electricity market in Texas, because it has a significant renewable growth potential and represents an island system. So it's not connected to any other grid. And we chose the year 2050 in order to be able to forecast a significant amount of renewables on the system. So we first assessed the potential for flexibility in 8 residential and commercial end-use loads. These loads don't necessarily need to be continuously running to meet customer needs, which is an important aspect. We used Rocky Mountain Institute's 2012 Reinventing Fire analysis to forecast the load by major end use in 2050 to parameterize the loads from each of the end use levers we used in the model. And this load forecast also integrated the additional load that we're expecting to see from electric vehicles. We also used Reinventing Fire's outputs to model the hypothetical 2050 generation mix in ERCOT. And this was able to let us forecast what the generation would be at an hourly level. And so we assumed 60% of this energy came from renewable energy, wind and solar specifically. 20% came from inflexible resources like geothermal, and the remaining 20% consisted of very flexible gas-fired generation. And so to calculate net load, we subtracted the power generated from solar and wind from total load for each hour. And then we simulated hourly load shifting from high net load hours to hours of high renewable availability using our identified 8 flexible levers over here. And once again, daily energy use was kept the same to maintain that same level of services to the customers. And so here is, this chart shows the impact that wind and solar have on total demand throughout a day in our forecast. So as you can see, this blue curve over here, that's our net load, which is our load without solar and wind generation. And this, as you can see, bellies out around midday and then quickly ramps up in the afternoon hours, hitting its peak between about 6 and 8 p.m. Many folks are probably familiar with the term the duck curve. This is exactly what it's showing. And so, how can demand flexibility address these concerns? So here we show what our suite of demand flexibility levers can deliver. As you can see, it significantly mitigates the concerns we saw on the last slide. This blue dashed line is that old net load curve, and this green line here, that is what our new net load curve looks like after we exercised our 8 flexibility levers. So as you can see, demand flexibility flattens this net load curve. It significantly brings down that peak, and it also reduces that afternoon ramping that folks have really discussed at length as being a potential problem. And so, as you can see, the contributions of our different end-use loads vary significantly. It also depended on the order we modeled each end-use load, and I will discuss that in a little bit. But as you can see, shifting electric vehicle charging and plug load use, for example, into the middle of the day really helps flatten this curve. So here are our calculated benefits from using demand flexibility. And so this is using that new net load curve presented on the previous slide. And again, this new net load is the result of shifting demand from times of high net load to times of high renewable availability. And so to get this value of renewable generation, we estimated the hourly clearing prices for wholesale energy based on matching the supply curve of dispatchable resources with hourly net load. And to get this value of renewable energy with flexibility, we matched our new net load curve with that same supply curve, which gives us that change in wholesale prices. Using this same supply curve, we were also able to estimate the change in annual curtailment on the system before and after demand flexibility is implemented. In our analysis, we assumed that renewable energy would be curtailed during the hours of the day when net load drops below 20% of annual energy supply. And that 20% represents the level of inflexible energy on the system. And so we found that curtailment was reduced by 40% as a percentage of load, and in whole terms, also it reduces net peak by 56%, I'm sorry, 24%, and that ramping then decreases by 56%. So a lot of impacts, a lot of great benefits, but we also need to discuss the other side of the equation, which is what does this all cost? So this chart shows, it's a supply curve, and it shows all 8 flexible levers we looked at. And so we looked at the cost of enabling flexibility in each technology. So sometimes that is a microchip, sometimes that is the actual storage, like ceramic bricks, for example, in our heating lever. And so we divided that cost by how many megawatt hours of curtailment we could avoid. And so this x-axis here, or the bar width, I would say, represents the load shifting potential for each lever, and we're representing this in gigawatt hour per year. And you're seeing here the total effect of each of the flexibility levers, the total potential of avoided curtailment out here. And this is an interactive effect. In order to avoid double counting, we basically were able to model each of the technologies in a successive manner. So all of these levers that you see on the right were modeled after the ones that came before it. And so this bar height is the annualized cost of avoiding 1 megawatt hour of curtailment for each of these levers. And this cost nets out the value of peak demand savings, since that is a significant benefit that needs to be considered when looking at the cost. And we calculated that peak demand savings by looking at the generation and the transmission and distribution that would no longer need to be built with demand flexibility on the system. And you must be wondering what these crazy negative numbers are, and that is, as I said, due to the significant impact that factoring in peak demand savings can have on lowering costs. And so I think it's important to show, to compare and contrast these demand flexibility levers, the portfolio of the demand flexibility levers with natural gas used for balancing renewables. And so we have seen a lot of utilities announce that, you know, yes, I will build renewable energy, but that means I also will build more gas generation in order to integrate those renewables on the system. And so this far left column here contains that annualized cost of the different demand flexibility levers that we modeled. These five, so there's about 5 low cost levers here, and then 3 a bit more expensive levers here. And once again, these were modeled after the other levers, and so that is why you're seeing such a varied price, in the sense that a lot of the flexible potential was soaked up in those previous levers. And why you don't see commercial heat as a more expensive lever is actually we found that there's winter peaks, that the commercial heating was well coincident with the peaks in winter, and so there was a significant opportunity for commercial heat to bring down those peaks. And so here's this cost-effective portfolio. So this is what we want to call the break-even point, where the costs of the portfolio of flexible levers are at a point where they provide more benefits to the grid than what they cost. And so this is what you see. This is about $400 million we'd see of avoided gas burn. And so that is due to the avoided curtailment, the gas that you would be building to integrate those renewables. And then we also have benefits due to the net peak reduction, which is more of the capacity. So this is the operations, and this is the actual capacity that is built in order to integrate renewables. I'm sorry, in order to meet peak load. Okay, and so overall, we think our analysis is fundamentally conservative, and I'm going to walk through why we think this is the case. And so first of all, we have a limited value stack. I just walked through the two values of flexibility that we calculated. We did not account for participation in ancillary service markets or decreased line losses, etc., that could add to the cost effectiveness of each of these flexible levers. We also didn't look at industrial load. Héloïse will be presenting on the industrial sector later in this webinar. In the past, industrial load has provided a great opportunity for demand response programs. However, we didn't have great data to use some industrial flexible end uses in this analysis. We also didn't use some new emerging low-cost technologies, such as blockchain-enabled plug loads and some of these more advanced control strategies used in high thermal mass buildings. These technologies would also lower the costs. And so what does all this mean? And so we identified 4 big takeaways. First of all, demand flexibility can really improve the efficiency and the optimization of system planning. Using demand flexibility from the onset in grid system planning, you can significantly avoid investment in gas generation and also other infrastructure investments to upgrade the grid. Demand flexibility should be integrated and thought of and considered when establishing renewable targets. A lot of folks say that there is a technical and economic limit to renewable penetration, and this target can be pushed up when you consider demand flexibility as well. Using demand flexibility while procuring renewable energy can improve the overall economics of the project by using such a cost-effective resource paired with the renewable energy on the system. Utility incentives are very important. Utilities need to have opportunities to make earnings off of non-capital investments, which demand flexibility would consist of. Performance-based regulation, for example, is one way to perhaps provide an incentive for utilities, but we want them to be able to see this as an opportunity and investment choice. And lastly, customers need incentives, and so this can come in the form of time-varying rate structures that improve the value proposition of buying these technologies or just participating in a utility program. There's also aggregator programs which basically can improve the relationship with the customer and how they are participating in these programs. And so that's it for me, and I will turn it back to Thomas.
Okay, thank you, Cara, for a very nice presentation. And we will now go through Héloïse's presentation. Héloïse is a consultant at Insight. She has a master's degree in business engineering and is a former Deloitte consultant. She is involved in various Enertop projects, which are industrial demand response projects. As Cara already mentioned, Cara explained the potential of demand response at a residential scale. And now Héloïse will give a presentation on the potential of demand response at an industrial scale, and then mainly the savings that can be made from the industrial perspective. So I'm going to hand over the control to Héloïse, and then you can start your presentation.
Okay, thank you very much. So good morning, good afternoon, and good evening to everyone. Thank you for joining. Thank you, Cara, for this really interesting presentation. So, okay, my name is Héloïse, and I'm senior consultant here at Insight, working mainly with electro-intensive industry to help them capture the potential value from energy flexibilities. And quickly about Insight. So Insight is a consulting company developing and providing advanced analytics solution in multiple areas, and we are really active in energy. So now I'm going to present you indeed more this time energy flexibility that we can find in the industrial sectors. So we all agree on the fact that energy flexibility is becoming key to turn energy transition challenges into a success. But the question is, okay, where to find these energy flexibilities? So should we find these energy flexibilities in the supply and maybe support or invest more into flexible power plants that enables to mitigate the fluctuation of renewable productions? Should we invest into a network and maybe ease the share of electricity between areas with different supply and demand situations? So for instance, increasing interconnection grids, but this is a high cost to be considered. Should we investigate into storages, improve the storage that allow finally a delay between the production and the consumptions? Or finally, should we focus on the consumption side with what we call the demand response and improve the willingness of the consumer level to adapt this energy, the electricity demand based on demand needs? And basically, I will really focus on the demand response, especially for the industries, because it exists a lot of flexibility, but also what we see is that there is a real incentive, in fact, to valorize these energy flexibilities. So in particular, demand response has a really big role to play. We estimated here in Europe a potential of 52.3 gigawatts. So it's quite important. And you can see here on the graph the waterfall of this potential spread into 3 categories. So you can find 30% of potential owned into the industrial sectors. You have also the tertiary, and then finally 40% owned in the residential. And Cara already explained and provided interesting information about how to leverage flexibility at residential side. So we really focus here on the industry and what are the potential value we can generate it with them. So when we speak about demand response management, there is 2 topics to be addressed. The first one is regarding the process, and the question is, where is in fact my flexibility? So it's really a question of identification of the energy flexibilities. Where is it? How to extract this one? What are the constraints behind this energy flexibility blocking me to operate my flexibilities? And then the second question after that is, okay, now that I have my flexibility identified, where can I valorize this one? And what is the value I can generate it from my energy flexibilities? So I propose to first present you a bit the type of energy flexibilities that we see in the industrial sectors. There is multiple different energy flexibility levers. Here is the top 5 that we see in industries. Cara already explained some of them, so I will just quickly recap the 5 I have here. So the first one is about the load shifting flexibility. So this is mainly when you have a process with an overcapacities. So basically the idea will be to shift the load and to push the consumption during the hours where the electricity is the cheapest, and the other way around when the electricity is the highest. The second example is about load reschedule. So basically here we are speaking about production planning where you have 2 types of product that is a specific consumption quite different. So basically you will produce the product that is the most electro intensive, especially when the price is really low, and again the other way around when the price is really high. The third element this time is what we call the load shading. Again, Cara slightly explained about these flexibilities. So here we look at this flexibility when we have no overcapacity. Basically, the process will run full time. So each time we decide to stop for an hour the process or for 15 minutes the process, it means that we have production loss to consider. So this needs to be done only with really high incentive. So typically when the price is really extremely high. A fourth element is what we call the fuel switching. So this time it's a real trade-off that we are looking for between fuel and electricity. As an example, in the pulp and paper industries, for the on the paper machines, you have the drying sections, and on the drying section, basically you have a possibility to dry the paper either with burners that are running on gas that will heat, in fact, the paper, or you can select also fans running on electricity that will ventilate, in fact, this heat. And here you have a real trade-off between using a full gases or a full electricity drying methods based on these electricity prices. A last flexibility that is often present in industries is about the CHP, so the cogenerations. So here we have a real possibility to modulate, in fact, the production of electricity towards the production of steam. And this can be done via some kind of bypassing processes and so on. So what I would like maybe to do with you is to show you an example with cement industries. So basically cement industries is done in 3 parts. So you have a first part, which is the kiln feed preparations in the blue one. The second part is the clinker production in orange. In these sections, you have the cement kiln running on gases that really cannot stop because of a really high cost of running on and off. And then after, you have the clinker grinding. This example is having electricity consumption of around 300 gigawatt hours per year, just for the informations. If I look now in terms of flexibility, what I see here is I have my raw mill that is an asset having an overcapacity of 40%. That is usually what we observe in the cement industries. We also see that the raw mill itself represents moreover 30% of the total electricity consumption of the site, around 10 megawatts. It's on-off principle, so no possibility to modulate this process. It's only switch on or switch off. So typically here, the type of flexibility we have will be to optimize, in fact, the raw mill planning based on the electricity prices by, in fact, leveraging this 40% overcapacity and also leveraging the up and downstream storages that you can see on the slides. Second, flexibility, the cement mill, same time of flexibility, in fact. We have an overcapacity of 40%. This time, interesting, we cover 40% of the total electricity consumption. So this is really important to mention. With only 2 extremely flexible processes, we are covering 70% of the total electricity consumption. So this is really a kind of promising industries. Regarding the maximum load, we are here around 15 megawatt, and again, not possible to turn to modulate, but only to turn off and turn on the machines. So again, we will optimize the cement mill planning based on these electricity prices. Industries, cement industries is one of the example, but there is plenty of other type of processes. We have mechanical pulp productions, for instance, compressors in hair separations, extrusions in petrochemical. I think about paper machines, industrial CHPs, even electric arc furnace in steel productions, and so on and so on. There is really a lot of different processes that are flexible. So now I think that we have a clear view on the type of flexibility that we have. Now the question is, okay, but where am I going to valorize my flexibility and really see to extract the most value from it? So basically there is many markets and many opportunities to valorize these energy flexibilities with different time frame. A first element is ancillary services. So basically there what we see, especially in Europe, more and more weekly and daily auctions reserve products that are introduced. And this brings a lot of new opportunities, in fact, to valorize your flexibilities. So here what we see is a real arbitrage between ancillary services and electricity markets. So basically, you really can optimize the volume you will provide on the reserved, but also optimize the reservation cost that you can offer, considering the potential that you could have generated on the electricity market. Another example is the day-ahead market. So basically what we observe on the day-ahead market is an increasing volatility of the day-ahead market, but also with more and more extreme prices for at least some countries. So here I created a table with showing some potential annual savings for two different flexibilities that you could generate for Belgium, France, Germany, and the Netherlands, just for you to have a view on this. So if, for instance, I take the load shifting, for instance, if I have a flexibility of 1 day per week, it represents more or less 3 hours every day. So basically, if I can avoid the 3 highest hours, I can save around, in average, 16,000 euro for each megawatt that I will shift. So basically, if I have a process like my raw mill process or my cement mill process, I will be able to shift between 10 to 15 megawatt. So I can multiply by 10 and 15 this potential savings. So it becomes quite interesting. Regarding the second flexibility, that I put a load shading example. So basically here I put an opportunity cost of 65 euro per megawatt hours being the threshold. So what I mean here is that if we go above this threshold, the process is not profitable anymore. So basically I have all interested to switch off my process at that moment. And here is the potential savings that you could have generated doing these actions. So you can go up to 20,000 euro per megawatt shed again for 1 year savings, especially for France and Belgium. What is interesting here to observe is that Germany and the Netherlands has less opportunities on load shedding, simply because extremely prices is really rare on this in Germany and also in the Netherlands. But there is a lot of other places where you can valorize your energy flexibilities. I think about real-time market, intraday market, balancing market, if applicable in the countries. But what is also interesting to observe is the fact that we have new markets, new flexibility platform that is emerging more and more. I think about, for instance, here in Belgium with Elia about the bid ladder. I see a lot of new initiatives. I think about, for instance, the local market initiatives in UK run by Centrica. I know that a lot of new companies are created. I think about Nordpool with a Nodes company developing power markets and so on. So all these new places where the flexibility can valorize will really increase, in fact, the potential industries, but not only industries, residential could generate it from their own flexibilities. So if I come back to my example in the cement industries, I will just use, for instance, the flexibility I had on my cement mill. So the idea will be to identify the peak hours and to avoid producing during the really high prices hours. I took here an example for the Belpact for Belgium. So remember, we had 40% of overcapacity. So this represents more or less around 10 hours per day of flexibility. So it enables me to avoid 67 hours, the most expensive hours over the week. So here you can see I put it orange threshold on the graph. So what you can see here is that if I'm above this threshold, I'm in the 67 hours, the most expensive. So during that time, my planning will look like this. So I will avoid producing during the really high prices. In terms now of savings, again, I have here the average prices for the Belpex market, which is around 44 euro per megawatt hours. If I remove the 67, sorry, if I remove the 67 most expensive hours, I drop to 36 euro per megawatt hours. So I can account more than 7 euro per megawatt hours of savings. And this ends into a total of, at maximum of course, but a total of 500 euro and 90,000 euro for a year, which is quite important. Of course, something important to consider here is the constraints, and maybe some opportunity will not be able to be captured because we have some technical constraints. And this brings me to the next slide, which is the fact that we need to consider the complexity. So optimal planning, it's okay, but we need to make sure that this one is realistic. So it's not only about electricity cost, but we need to consider industrial constraints, so technical constraints, economical, and of course commercial constraints. And also regarding the objective, it's not only about reducing the electricity cost, but it's also looking at the storage cost, looking at the operational cost, and energy bill in general. Finally, something also important to consider is the reactivity, because the reactivity of this flexibility will drive the places actually where I will be able to valorize my flexibility. Providing a flexibility on the balancing require me to be quite reactive within 5 to 15 minutes that I will not be always able to do on other flexibilities. And then to conclude, regarding the potential of industry, so we know we have an increasing potential of energy flexibilities in the industry sector. Something still to mention is the fact that there is still more to unlock. So the first element is that we know there is a potential in terms of flexibility. We know that a lot of processes are flexible. Something also interesting is that more and more industries are having a flexible contract. So having in fact this incentive to valorize this flexibility. But unfortunately, by experience, we see still a lot of industry that are still under a fixed contract, which can be problematic to provide this flexibility on the market. Second element is the fact that some of the processes and some of the flexibility generated enough value to be offered on the market, but still some other flexibility is not valorized enough, and so the industry retain from providing this energy flexibility on the market. So there is still to be unlocked. And now to talk about a bit the drawback and the blocking point, retaining industry to leverage the potential themselves is, as I mentioned before, the multi-objective aspect. So it's not always easy to look at optimization and consider either the electricity cost, but also other type of objective in the same optimization. And finally, when we speak about industrial energy flexibility, it comes always with really complex technical, economical, and commercial constraints. And those need to be considered to make sure that anytime we suggest to valorize an energy flexibility, it doesn't come with negative impacts. So in fact, that was it for my presentation. So thank you very much for the attentions. And I will just give back the floor to Thomas.
Thank you, Héloïse, for a very interesting presentation also. So now it's time for the Q&A. Please also keep sending the questions. We have quite some time left for questions. And on the screen now you see my email address and my phone number. If you have any questions regarding this webinar or regarding the Energy Flexibility Forum in June in Copenhagen, please feel free to drop me an email or call me anytime, and I can answer any questions regarding the program or other opportunities there. So for the first question, which is sent in by Geert, which is for Cara, what is the percentage of electric cars in the total car fleet that you took into account for the study?
Yes, that's a great question. And so for EVs, we assumed that there would be 11.5 million vehicles on the road. And where we got that was the Bloomberg New Energy Finance projections as a percentage of total vehicles. I don't have that answer, I'm sorry, but I can find out and send you a response after this phone call.
Okay,
I'm sorry,
great.
webinar.
Then you can. It's possible to send me an email, and then I will forward the question to Cara and connect you to answer this question. So the next question is for Héloïse, which is sent in by Alex. How to include demand flexibility in the utility grid planning when it's based on customer adoption? So for example, electric vehicles, what happens if we don't reach the EV penetration that is expected, or if industries are not able to deliver the flexibility? How can you then include it in the planning?
So sorry, so what do you mean? Do you mean how we are doing so far even if the industry are not capable of providing such type of flexibility?
Yeah, I think what Alex means is when you're planning the utility grid, how can you make sure that demand response programs are reliable sources of flexibility?
Okay. Regarding the industries, it's quite simple. So basically, we are always basing ourselves on the real-time information from the industry to make sure that it's always flexibility that can be taken into account and that will not create any problems for the rest of the production planning, so that this flexibility can be offered on the market. Of course, if we are speaking about valorizing this flexibility on the direct market, this is not something that, it's something that is done directly on the market. But regarding flexibility that is offered directly at utilities, then the flexibility is guaranteed to be available for any aggregators that is operating the flexibilities and so on.
Okay, great, thanks. And maybe also for Cara, because of course Héloïse looks at it from an industrial perspective, but Cara, could you also answer that from a residential perspective? And for example, with e-mobility integration, what happens if the EV penetration isn't one expected? Would that change it for the utility grid planning?
Yeah, of course, when you're using these resources in planning, that you can never be totally sure what the level of adoption is going to be. I think though that there has been, we look at previous demand response programs that have been able to deliver that assumed reduction in energy use when the utilities have planned for it. In our study, we really wanted to look at what could the potential be with demand flexibility at like full deployment, and so that is the assumptions we were using. But I think that in planning scenario, there's going to be a multiple scenario case that you would want to integrate and consider. It also depends on, as I said, the customer incentives available. Folks are going to be more inclined to smart charge or charge their EV if they are on time varying rates where they can actually it would be less expensive to charge during times of day and the other, and so they'll want to interact with the grid in that way.
Okay, great, thank you. So the next question is for Héloïse. The question comes from Costa. Do you operate also in the flex market with residentials, so the market that Cara explained more about? And if yes, could you provide some more info? Or if no, could you tell us why not and why only industrial demand response?
Yeah. Well, actually, regarding the residential, at residential level, we are not doing as much as we are doing for the industries, except regarding the EV. So we are having also some solutions to optimize, in fact, charging of the EVs. And this is where indeed we have a lot of opportunities. For the rest of the flexibilities optimization within the residential, the reason why we are not really focusing there is really a question of incentive so far, especially in Belgium, but it's moving. We really see a lot of supplier trying to provide flexible contract to also residential, but it's really question of incentive. They don't have any incentive to optimize and to provide this energy flexibility so far. So difficulties to create value to the residential.
Okay, thank you. And then a question from Roberto, also for you, Héloïse. To realize electrical flexibility is the method for choosing electric loads with different priorities respecting the planning of energy usage in accordance with the balancing service provider or the equivalent of the balancing authority.
Well, sorry. So to see what is the potential savings, what is the potential on the balancing, because basically not all the country has the possibility to really valorize potential on the balancing. So
yeah, I think what he's asking here is well, the method of choosing the electrical loads and the different priorities there, is that respecting the planning of the balancing service provider or the balancing authority?
Yeah. Well, the thing is, when we optimize, in fact, the energy flexibilities, we look at the valorization that we can generate it both on directly energy market, but also with services or in services that is generated by, for instance, some aggregators and so on. So of course, it's the question of potential savings that you can generate on both sides. Of course, if a reserve market or ancillary services is more interesting compared to the potential generated on a day ahead, of course, you cannot sell your flexibility on both sides.
Okay, great. I think that answers the question. So, well, it's 5 o'clock now, so we have to end this webinar. If you have any questions, please feel free to email me, and I can forward to Cara or Héloïse and make sure the questions will be answered. Cara and Héloïse, thank you for doing the presentations. I think it was a very interesting webinar, and I hope to see you all in Copenhagen on the Energy Flexibility Forum this coming June. Thank you.
Great, thank you.
Thank you very much.